Hey everyone, how goes it, and welcome back to Computer Science 311. Today, we're going to discuss processes. Early computers only allowed one program to be executed at a time. This program had complete control over the system and had access to all of the system's resources. Now today, computer systems allow multiple programs to be loaded into memory and executed concurrently. A question starts coming about when discussing operating systems, and it's simply, what do we call these CPU activities? Early on, computers were considered batch systems that executed what we called jobs. Now, following that was the emergence of time-shared systems that ran user programs, otherwise known as tasks. These terms didn't quite sufficiently describe what we're referring to, because like a single user system, a user may be able to run several programs at one time. And even if the computer can only execute one program at a time, such as an embedded system, that does not support multitasking. The operating system may still need to support its own internal programmed activities, such as memory management. Now, all of these activities are extremely similar, so we refer to them simply as processes. A process is a unit of work in most modern computing systems. And therefore, a system consists of a collection of many processes, some executing user code, others executing operating system code, and potentially all these processes can execute concurrently with the CPU or CPUs multiplexing among them. The status of a current activity of a process is represented by a value called the program counter, and also the contents of the process's registers. Now, these sections include the text section, so that's all the executable code, the data section, all the global variables, a heap section, so that's the memory that's dynamically allocated during a program's runtime, and also the stack section, and this is temporary data storage when invoking functions, such as function parameters, return addresses, and also local variables. Now, a program is a passive entity. Only when it starts executing does it become a process, which is the active version. Now, here's how we can represent a process into memory. Now, notice the sizes of the text section and the data sections are fixed. Their sizes do not change during the program's runtime. However, the stack and the heap sections can shrink and grow dynamically during the program's execution. Now, each time a function is called, an activation record containing the function's parameters, local variables, and return addresses are pushed onto the call stack. When control is returned back to the function, the activation record is popped off the stack. Now, in contrast, the heap will grow as memory is dynamically allocated and will shrink when memory is returned to the system. The stack and the heap sections grow toward one another. Now, the operating system must ensure that they do not overlap one another. Here's an example program and what the process would look like in memory. Now, as a process executes, it changes states. The state of a process is defined in part by the current activity of the process. Now, some of these states can include new, so this is the process being created. Running, instructions are being executed. Waiting, the process is waiting for some sort of event to occur, such as an I/O completion or reception of some kind of signal. Ready, the process is waiting to be assigned to a processor. And finally, terminated. The process has finished execution. Now, it's important to realize that only one process can be running on any processor core at any instance. Now, looking at this state diagram, you can see all of the different states that the process can take. So when it is new into our system, it's being created. Once it's been created, it then gets admitted to the ready queue. Now, once it's in the ready queue, It's then scheduled by a dispatcher into the running state. Once it's in the running state, if it has some sort of I/O or some sort of wait event, it goes into this waiting state, which then once it completes, it goes back to ready, then back to running. Now, as it's running, once the process has finished executing, it transitions to the terminated state. Now, each process is represented in the operating system by a structure called a process controlled block, PCB. Now, this is also sometimes referred to as the task control block. Now, it contains many pieces of information associated with the specific process, and some of these include the process state. So once again, that's the state of the process, so that could be new, ready, running, waiting, and also terminated. It also contains a program counter. This counter indicates the address of the next instruction to be executed for the process. CPU registers. The registers vary in number and type depending on the computer architecture. They include accumulators, index registers, stack pointers, and general purpose registers, plus any conditional code information. Along with the program counter, this state information must be saved when an interrupt occurs. This is to allow the process to be continued correctly after when it is rescheduled to run. CPU scheduling information. This information includes a process's priority, the pointers to the scheduled queues, and any other scheduling parameters. Now, we talk about this more in a future chapter. Memory managed information. This information may include such items as the value of the base and the limit registers, and the page tables or the segment tables depending on the memory system used by the operating system. There's a lot more detail about this that we'll explore later on. Accounting information. This information includes the amount of CPU and real time being used, the time limits, accounting numbers, jobs or process numbers, and so on. Input-output status information. Now, this information includes the lists of I/O devices allocated to this process, a list of the open files, and so on. The PCB simply serves as a repository for all of the data needed to start or restart a process along with some accounting data. Now, what we have described so far has implied that the process of a program only performs on a single thread of execution. However, most modern operating systems have extended the process concept to allow a process to have multiple threads of execution and thus perform more tasks at a time. This is very beneficial on a multi-core system where multiple threads can be run in parallel. The PCB is then expanded to also include the information for each one of the threads. Now, the objective of multi-programming is to have some process running at all times, so that way we maximize the CPU's utilization. The objective of time sharing is to switch a CPU core among the processes so frequently that users can interact with each one of the programs while they're running. In order to do this, we introduce the process scheduler, which selects an available process for program execution on a core. CPU cores can only run one process at a time. So this indicates for a system with a single CPU core, there will never be more than one process running at a time, whereas multi-core systems can run multiple processes all at one time. Now, the degree of processes currently inside of memory is known as degree of multi-programming. Now, in general, most processes can be described as either an I/O-bound or a CPU-bound process. An I/O-bound process is one that spends more of its time doing input and output rather than spending doing computations. And of course, a CPU-bound process generates less I/O requests and uses more time on the processor. Now, as these processes enter the system, they are put into some data structures, one of which is called the ready queue. This is where the processes are ready and waiting to be executed on one of the CPU's cores. The queue is generally stored as a linked list, and a ready queue's header contains the pointers to the first PCB in the list, and each PCB that includes a pointer field that points to the next PCB in the ready queue. Now, the system also includes additional queues. For instance, suppose that a process makes an I/O request to a device such as the hard disk. The process will have to wait for the I/O to become available. Processes that are waiting for a certain event to occur, such as I/O completion, are then placed into a waiting queue. Now, processes move among a lot of the various queues that we have in the system. This is one way that we can view the ready and the waiting queues as a linked list. Now, this is a common representation of process scheduling that's called a queuing diagram. The circles represent the resources that serve the queues, and the arrows indicate the flow of the process in the system. A new process is initially put into the ready queue, and it waits there until it's selected for execution, otherwise known as dispatched. Now, once the process is allocated to a CPU core and is executing, one of several events can occur. The process could issue an I/O request, and then be placed on the I/O wait queue. The process could create a new child process, and then be placed on the wait queue while it awaits the child's termination. The process could be removed forcibly from the queue as a result of an interrupt or having its time slice expire, and then be put back onto the ready queue. In the first two cases, the process eventually switches from the waiting state to the ready state, and then is put back into the ready queue. A process will continue the cycle until it terminates, at which time it is removed from all of the queues and has its PCB and resources deallocated. Taking this concept a bit further, interrupts cause the operating system to change a CPU core from its current task to the running kernel routine. When this interrupt occurs, the system needs to save the current context of a process running on the CPU core, so that we can restore the context whenever the processing is done, essentially suspending the process and then resuming it. Generally, we perform what's called a save state of the current state of the CPU's core, be it in kernel or user mode, and then a state restore resumes the process. Switching the CPU core to another process requires performing a state save of the current process and a state restore of a different process. This is known as context switching. The thing that we do have to keep in mind is context switching is pure overhead. The system is not doing any useful work while it's switching these different processes. In order to do context switching, this depends heavily on hardware support. Some processors provide multiple sets of registers to do this. Here's an example of a context switch, where basically, if we have this process control block of 0, this state is saved, and then we reload a PCB into here, execute that. Once it's done, or some sort of I/O request or whatever happens, then we have to save the contents of this one, and then we reload the state from PCB 0. One of the big takeaways from this is doing this requires overhead. We're not running PCB 0 or 1. We're just switching the context. Now, the process in most systems can execute concurrently, and they may be created and deleted dynamically. During the course of execution, a process may create several new processes. The creating process is called the parent process, and the new processes created are called the children. Now, each one of these new processes may in turn create other processes, forming a tree of processes. Now, most operating systems identify a process according to a process identifier, or a PID, which is typically just an integer value. In general, when a process creates a child process, that child process will need certain resources, like the CPU, memory, files, or I/O devices, in order to accomplish its task. A child process may be able to obtain its resources directly from the operating system, or it may be considered to be a subset of resources from the parent's process. Restricting a child process to a subset of the parent's resources prevents any process from overloading the system by creating too many child processes. Now, when a process creates a new process, there are two possibilities for the execution. First, the parent continues to execute concurrently with its children. Or alternatively, the parent has to wait until some or all of the children's process has terminated. There are also two address space possibilities for the new process. First, the child process is just a duplicate of the parent process. Or alternatively, the child process has a new program loaded into it. Now, in order to see this, in Unix, as we've seen, each process has an identifying process identifier, the PID, which is a unique integer. A new process is created by a system call called fork. Now, the new process consists of a copy of the address space of the original process. This mechanism allows the parent process to communicate very easily with its child process. Now, after fork is called, one of the two processes typically uses the exec system call to replace the process's memory space with a new program. Now, in this matter, the two processes are able to communicate and then go their separate ways. The parent can then create more children, or if it has nothing else to do while it's waiting for the child to run, it could issue another system call called wait to move itself off of the ready queue until the termination of the child. Because the call to exec overlays the process address space with a new program, exec does not return control unless an error occurs. Here's a tree process inside of Linux. So this are processes that have created children processes. Notice that the systemd process, which always has the PID of 1, serves as the root parent process for all user processes and is the first user process created when the system boots. Now, once this has happened, systemd process creates processes which provide additional services such as web or print services, an SSH server, and the like. A process terminates when it's finished executing its final statement and asks the operating system to delete it by using the system command exit. At that point, the process may return a status value, typically an integer, to its waiting parent process via the wait system call. Resources of the process, including physical and virtual memory, open files, I/O buffers, are then deallocated and reclaimed by the operating system. A parent may terminate the execution of one of his children for a variety of reasons. One of those is the child has exceeded its usage of some resource that has been allocated. Another, the task is assigned to the child is no longer required. And finally, the parent is exiting, and the operating system does not allow child to continue if the parent terminates. Some systems do not allow a child to exist if its parent has been terminated. In such systems, if a process terminates, either normally or abnormally, then all of its children must also be terminated. This phenomenon is referred to as cascading terminations, and this is normally initiated by the operating system. In addition, a parent process may wait for the termination of a child process by using the system call wait. The wait system call is passed a parameter that allows the parent to obtain the exit status of the child. Whenever a process terminates, its resources are deallocated by the operating system. However, its entry in the process table must remain there until the parent calls wait. This is because the program table contains the process's exit status. Now, a process that has terminated, but whose parent has not called wait, is known as a zombie process. Now, all processes transition to the state when they are terminated, but generally they exist as zombies only briefly. Once the parent calls wait, the process identifier of the zombie process and its entry in the process table are finally released. Now consider what would happen if a parent did not invoke wait and instead just terminated, thereby leaving some processes behind. These are referred to as orphan processes. Now, processes executing concurrently in an operating system may be either independent processes or cooperating processes. A process is independent if it does not share data with any other process executing in the system. Now, in contrast, a process is cooperating if it can affect or be affected by other processes executing in the system. Now, there are several reasons for providing an environment that allows process cooperation. First, information sharing. Since several applications may be interested in the same piece of information, for instance, think about copying and pasting, we must provide an environment to allow concurrent access to such information. Computation speed. If we want a particular task to run faster, we must break it into subtasks, each of which will be executing in parallel with the others. Modularity. We may want to construct a system in a modular fashion, dividing the system functions into separate processes or threads. Cooperating processes require an inter-process communication, an IPC mechanism that will allow the exchange of data. Now, there are two fundamental models of these inter-process communications: shared memory and message passing. Here's an example of both shared memory and message passing. Both of the models just mentioned are very common in operating systems, and many systems implement both. Message passing is very useful for exchanging smaller amounts of data because no conflicts are needed to be avoided. Message passing is also easier to implement in a distributed system that's shared memory. Message passing is also easier to implement in a distributed system rather than shared memory. Now, shared memory can be faster than message passing since message passing systems are typically implemented using system calls, and thus require more time-consuming tasks or a kernel intervention. In shared memory, system calls are required only to establish the shared memory registers. Once the shared memory is established, all access are treated as routine memory access, and no assistance from the kernel is required. Now, inter-process communication using shared memory requires communicating processes to establish a region of the shared memory. Typically, a shared memory region resides in the address space of the process creating the shared memory segment. Other processes that wish to communicate using the shared memory segment must attach themselves to the address space. The processes are also responsible for ensuring that they are not writing to the same location simultaneously. In order to illustrate the concept, what we do is establish what's called a producer and a consumer problem. A producer process produces information that is consumed by a consumer process. Now, one solution to the producer-consumer problem uses shared memory. This allows the producer and the consumer process to run concurrently. In order to allow the producer and consumer process to run concurrently, we must have available a buffer of items that can be filled by the producer and then emptied by the consumer. This buffer will reside in a region of memory that is shared by the producer and the consumer processes. A producer can produce one item while the consumer is consuming another item. The producer and consumer must be synchronized so that the consumer does not try to consume an item that has not yet been produced. In order to implement this, we have to recognize that there are two variations on this kind of buffer. One is an unbounded buffer that places no practical limit on the size of the buffer. The consumer may have to wait for new items, but the producer can always produce a new item. In contrast, the bounded buffer assumes a fixed buffer size. Now in this case, the consumer must wait if the buffer is empty, and the producer must wait if the buffer is full. Now another way to achieve the exact same effect is for the operating system to provide the means for cooperating processes to communicate with each other via message passing. Message passing provides a mechanism to allow processes to communicate and synchronize their actions without sharing the same address space. It is particularly useful in distributed environments where communication processes may reside on a completely different computer. Now, message passing is facilitated by at least two operations: send and receive. Messages sent by a process can either be fixed or variable size. Now suppose we have two processes P and Q that want to communicate. They must send messages to and receive messages from each other via a communication link. Now we have to consider, what are the issues with implementing something like this? So how are the links established? Can a link be associated with two or more processes? How many links can there be between every pair of communicating process? What is the capacity of the link? Is the size of the message that the link can accommodate fixed or variable? And is a link unidirectional or bidirectional? Now, we're not going to focus heavily on the physical implementation of this communication link, but we are going to look at the logical implementation of the communication link. Now, there's several ways that we can implement this logically. First, are we going to choose direct or indirect communication? Second, are we going to choose synchronous or asynchronous communication? And third, is it automatic or explicit buffering? Looking at each one of these a little further, under direct communication, each process that wants to communicate must explicitly name the recipient or sender of the communication. In this scheme, the send and receive primitives are defined as the follow: send with the process P with a message, and receive with the process Q and a message. Keep in mind, in the first one, the P corresponds to the process that we're sending the message to. Receive indicates where we receive the message from. Now, in order to do it this way, a communication link in this scheme has to have the following properties. A link is established automatically between every pair of processes that want to communicate. The processes need to know only each other's identity to communicate. In addition, a link is associated with exactly two processes. And also, between every pair of process, there exists exactly one link. Now, what we have described is the scheme exhibits what we call symmetry in its addressing. That is, both the sender process and the receiver process must name the other one to communicate. A variant of this scheme employs asymmetry in addressing. Here, only the sender names the recipient. The recipient is not required to name the sender. The disadvantage in both of these schemes, symmetric and asymmetric, is limited modularity of the resulting process's definitions. Now let's consider indirect communication. With indirect communication, messages are sent and received from a mailbox or a port. Now in this scheme, communication links have the following properties. A link is established between a pair of processes only if both members of the pair have a shared mailbox. A link may be associated with more than two processes. Between each pair of communicating processes, a number of different links may exist, with each link corresponding to a mailbox. The operations required to do this is first we have to create this new mailbox. Then we send and receive the messages through the mailbox, and then finally, once communication has completed, the mailbox is deleted. Now in contrast, the send and receive primitives look like the following, where you send a message to a mailbox A, or you receive a message from mailbox A. Now we have to suppose that if we have processes P1, P2, P3 may all share the same mailbox A. Processes P1 sends a message to A, where both process 2 and 3 execute the receive from A. Which process will receive the message sent by P1? This answer depends on which of the following methods we choose. Do we allow a link to be associated with two processes at most? Do we allow at most one process at a time to execute receive operations? Or do we allow the system to select arbitrarily which process will receive the message? That is, either P2 or P3, but not both will receive the message. Now the system may define an algorithm for selecting which one of these processes will receive the message. For example, round robin, where the processes take turns receiving the messages. The system may identify the receiver to the sender. Now we further this by discussing synchronization. Message passing may either be blocking or non-blocking, known as synchronous and asynchronous respectively. Now looking at each one of these, a blocking send, this is the sending process is blocked until a message is received by a receiving process. A non-blocking send, on the other hand, this is the sending process sends a message and resumes an operation. Blocking receive, the receiver blocks until the message is available, and non-blocking receive, the receiver retrieves either a valid message or null. Different combinations of send and receive are possible when send and receive are blocking. Then we have a rendezvous between the sender and the receiver. Now, whether communication is direct or indirect, message exchange by communicating processes reside in a temporary queue. Basically, such queues can be implemented in these ways. Zero capacity. The queue has a maximum length of 0. Thus, the link cannot have any messages waiting in it. In this case, the sender must block until the recipient receives the message. Bounded capacity. The queue has a finite length, let's call it n. Thus, at most n messages can reside in it. If the queue is not full when a new message is sent, the message is then placed in the queue, and then the sender can continue executing without blocking. The link's capacity is finite, however. If the link is full, the sender must block until the space is available to queue. Also, unbounded capacity. Now, the queue's length is potentially infinite. Thus, any number of messages can wait in it, and the sender never blocks. Now, there are a lot of implementations of this inter-process communication. One very common one is called pipes. Now, pipes act as a conduit that allows two processes to communicate. Now, the issues that we discover with this is the communication unidirectional or is it bidirectional? In the case of two-way communication, is it half or duplexed? There also must exist a relationship, parent-child, between the communicating process. Do we have to have a relationship, like parent and child, between the communicating processes? And can pipes be used over a network? Two versions of this are named pipes and ordinary pipes. Now, ordinary pipes cannot be accessed from outside of the process that created it. Now, typically, a parent process creates a pipe and then uses it to communicate with a child process. Named pipes can be accessed without the parent and child relationship. Now, another way we can look at this is this concept called a socket. A socket is defined as an endpoint for communication. A pair of processes communicating over a network employs a pair of sockets, one for each one of the processes. A socket is identified by an IP address, concatenated with a port number. In general, sockets use client-server architectures. The server waits for incoming client requests by listening to a specific port. Once the request is received, the server accepts connection from the client socket to complete the connection. Now, one of the most common forms of remote service is called the Rpc Paradigm, the Remote Procedure Calls, which was designed as a way to abstract the procedure call mechanism for use between systems with network connections. Now keep in mind, a port in this context simply is a number included in the start of the messaging packet. The RPC system hides details that allows the communication to take place over what's called a stub on one of the client's side. This stub locates the port on the server and then marshals the parameters. The stub then transmits a message to the server using message passing. Now, parameter marshalling addresses the issue concerning different data representations on the client and the server machines. Consider the representation of 32-bit integers, for instance. Some systems use what's called Big Endian, and that stores the most significant byte first, while other systems use Little Endian to store the least significant byte first. Now, in order to resolve the differences like this, many RPC systems define a machine-independent representation of data. One such representation is called the External Data Representation, the XDR. Now, in this chapter, we have discussed what a process is, and that is a program in execution. We've also laid out the process in memory represented by 4 different sections: the text section, data, heap, and the stack. We also discovered that processes contain state information, where a process can be ready, running, waiting, terminated, or new. We then discussed the structure called a PCB, a process control block, and it is a way that we represent the processes in the operating system. From there, we also discussed how processes can communicate with one another. Now that we understand what a process is, we're going to continue to explore concepts related to it in much more detail. And until then, I'll see you next time.